All right, now we're going to take a look at a couple of application word problems that force you to use linear equations and some of the tools that we've talked about. So in this video in particular, we're going to look at how do we build two linear equations and determine when or if they're going to intersect, and then what does that physically represent. We've in the past videos already talked about how to identify when lines intersect. When we look at word problems or real life applications, we have to build the linear equations themselves. So I'm going to go through the steps to do that. I know this video is a few months after the past video. Our students just finished their semester, so I apologize for the delay there. But we'll start ramping up more application videos and some of the other concepts in math that will help prepare you for college engineering. When we look at straight lines intersecting, what we can see and remember is that on before the intersection, let's say these are my two lines, the red and blue lines. Okay, on this side here, the red line is above the blue line. After, you can't really see because my hand's in the way, but after they intersect, the blue line is now above the red line. Now that sounds like a very trivial point, but when we give physical meaning to the y-axis and the x-axis of a graph and our straight lines, then the point of intersection actually has true meaning, right? True physical meaning. So how do we think about this? So I'll give you an example and then we'll work through that example. And a very tangible example is something related to money. So this could be profits, and in this example, it's going to be costs, how much something costs to make. So in this scenario, we're going to imagine that you're a manufacturing manager and you have a product that you produce, and every day the product requires 4 workers to produce this. Each of your workers are paid $25 per hour, but you're hoping to cut costs in this manufacturing process. So you try and look for an alternative solution. And what you find is that there's a machine. This machine costs $1,500 to buy, right? And it can do the same job as the 4 workers, so it meets your need. It requires a skilled operator, so none of the 4 workers can operate this machine. So you need to pay someone else $50 an hour to operate this machine. And the machine costs some money for operation, right? Electricity and maintenance if you need to fix some components. So overall, we say about $25 per day to maintain and operate this machine. And let's assume that a workday is 8 hours. Well, what we're going to do is try to use this linear equation, y equals mx plus b, and try to use it to help determine, is it worth investing in this machine, right? So you can do this mathematically by setting up this equation, and then we'll see how we can visualize this graphically. So both are important, right? So for you, as you're solving things, maybe mathematically makes the most sense, but if you're trying to talk about these kind of concepts to your boss and giving a presentation, showing it graphically is also very important. And at the end of this analysis, we want you to know, we want you to be able to say financially, is it worth it to invest in this machine? Okay, so now I'm going to walk you through the 3 steps to build the linear equations, and then in the next slide we'll look at how do we compare those linear equations. So our objective here is to look at case A, where we have the 4 workers, in case B, where we have the machine and the 1 operator, and help determine what linear equations will help us in comparing to determine whether or not it's worth investing in this machine. So the very first step, we have to determine what the units or what the physical representation of my variables are. In this case, when we look at a linear equation or a 2D plot, right, x and y plot, we have to determine what these horizontal and vertical axes represent, right? The vertical y and the horizontal x axes. These will represent the data points at various components for your y equals mx plus b equation. So how do we determine this? Well, in general, the vertical axis, the y-axis, is what you want to compare. And the horizontal axis, the x-axis, is what you allow to vary. Okay, so I think the y-axis is a little bit more apparent, right? We're trying to determine which one, where do we have an advantage in costs, right? So the y-axis, or y variable in this case, will be our costs, or have units of dollars, right? The horizontal axis is what we want to vary. Well, I want to know, do these lines intersect, right? Is there a time where case B will eventually be cost savings? I know initially I'm going to have a loss because it cost me money to purchase the machine, but I don't know if eventually the machine will be worth it. So the x-axis is the variable component. A lot of times it's time. In this case, it is time. Sometimes it might be a length scale, or like a voltage component that you're varying. In this case, it's time. So it's up to me to determine what unit of time I want to use. Do I want to use seconds? Do I want to use hours? In this case, I choose days. I want to see how many days does it take to make this worth it. If it takes a lot of days, it might be worth switching it over to weeks or months, or however the problem might present itself. But in this case, I'm going to use days. All right, so I have y in dollars and x in time of days. All right, great. Step 1's complete. Step 2, now I have to give kind of the similar concept. I have to determine the units and give physical meaning to the parameters. My parameters are m, the slope, and b, my y-intercept. Well, a couple things. So we can look, I'll switch the order here. Let's look at the y-intercept. Well, for this equation to be true, every set of terms needs to have the same units. Like the y term needs to have the same units as the product of m and x term, needs to have the same units of the b term, because they're just added together, right? When you have terms that are added or subtracted, each of those terms, if they're in an equation, must have the same set of units, right? So the components. So since y is in dollars or costs, b, the y-intercept, must also be in dollars or costs. So I know the units are going to be in dollars. What does it physically represent? Well, y-intercept is when the line intersects the the y-axis. So when time is 0 days, at 0 days, that represents a capital cost, right? So initial cost before any hourly cost is put on. So it's a capital cost. That's why y-intercept is capital cost on day 0, and it's in dollars. The slope, m, how do we determine what the units are there? Well, I know that m times x has that product, that unit product needs to have a unit of dollars as well. I know x has a unit of days, so dollars per day for the slope times days for the x variable will give us a product of dollars. So the slope is a rate term, right? Whenever you have the x-axis representing some scale in time, the slope is a rate term. So what does that mean? That means a per time scale component. So it's dollars per days, right? So it's cost per day concept, right? Great. So now we're finished with step 2, and then now we can start working on step 3, which is actually determining what m and b are for each of these different cases. So we can start off by looking at case A. Case A, remember, that's when we have 4 workers and we have a cost per hour for each of these 4 workers. All right, so let's walk through this step by step. So remember, the y-intercept is the capital. Well, according to this scenario, there is no capital for hiring these 4 workers. So my capital, my y-intercept, would be 0. We start off with cost of $0 for day 0. To determine the slope, we know that we need to find something that's on a dollars per day perspective for all workers combined, right? So I say I have 4 workers, right? Multiply that by the cost per hour, $25 per worker per hour, and then multiply that by the workday, 8 hours per day, right? So I don't know if you've had experience doing unit conversions. This is an example of one. We'll do more examples of them in future videos. But the way to check is to see what your units cancel out to be, right? So 4 workers, that workers cancels out with the per worker component, right? That's kind of like dividing it by the term worker. Per hour here times an hour component, so that cancels out. So then this makes it $800 per day, right? So for this whole group of 4 workers, it costs me $800 per day to pay them. So my linear equation would simply be y equals 800, right, the slope, times x plus 0 for the y-intercept. So just 800x. Great. Now we're going to do the same thing for case B. Right? So case B, my y-intercept here is not 0. My y-intercept has the initial capital of paying for the machine of $1,500. So my y-intercept is 1,500. The slope has 2 parts, right? The 2 parts are for the operation and maintenance of the machine, which is $25 a day, and then the operator costs, right? $50 per hour. So we'll first look at the operator. It's a single operator, so we can say $50 per hour times the 8 hours per day. So I want to convert these to all be on a per day basis, so the units are consistent. So that gives me $400 per day for this operator. And then the machine operation and maintenance is just $25 per day. That's what we're given. So the total slope is just the sum of these two. So the slope is $425 per day. So I have my linear equation for case B. So the slope, $425 times x plus $1,500, right? So I have my 2 linear equations. Now in the next slide, we're going to compare. Okay, so we have our 2 linear equations, 800x and 425x plus 1,500. Now, first thing to ask ourselves is, do these lines intersect? And if they do they intersect in a way that's physically meaningful? So we have 2 linear equations. First, do they ever intersect? I know the slopes are not equal to each other, right? 800 and 425 are not the same, so they're not parallel. If they're not parallel, they will intersect somewhere, right? So yes, they will intersect. Second question is, do they intersect in a physically meaningful place? So what does that mean? If these lines intersect at a negative x value, that has no physical meaning to us for this problem, because a negative x value means before day 0. So that means nothing to us. So how do we determine if these lines are going to intersect at a negative or positive value? I know they're not going to intersect at x equals 0 because the y-intercepts are different. So how do you determine that? Well, first you can look at the y-intercepts. Case B's y-intercept, 1,500, is larger than case A's y-intercept of 0. So I know case B is going to start up higher than case A. Then I'm looking at the x in the x direction, so that I can look at the slope. Both slopes are positive values, so they're both growing values. Okay, so the case B starts off higher, right? 1,500. It's growing, right? 425. That's the rate, right? Dollars per day. That's slower than the rate that case A is growing, $800 per day, right? That's the slope. So case A starts up here, case A starts down here, case B starts up here, and case B grows slower than case A. So case A eventually will catch up to case B. So yes, they will intersect. yes, they will intersect in a positive x location, right? So all that's important. Now, thinking about it just from looking at slopes and y-intercepts takes some time. So if it's difficult, you can play around with the different scenarios. I think I've talked about this briefly in a previous video. Look at that. And also just drawing out all the different scenarios will really help you. So how do we determine when these lines intersect? Remember, when these lines intersect is when the x values and the or at what x values these y values will be the same. So all I need to do is just equate these two equations. So 800x is equal to 425x plus 1500, right? Then all I need to do is solve for x. So I can subtract 425x on both sides. So I get 375x is equal to 1500. And I divide 375 from both sides. So x is equal to 1500 over 375, which is equal to 4. So what does that tell me? Well, what does x represent? X represents time in days. So this means that the cost of case A and case B will be the same after 4 days. Okay? After that, it will be worth your investment for case B. So if your manufacturing process takes more, you're going to keep this process for more than 4 days, it is worth investing in the machine. Now, cutting jobs and all that stuff has a different ethical component, but this is just looking at the financial aspect of it. So on the next slide, we can take a look at a graph to see how that visually is represented. All right, so let's see graphically what this looks like. So this blue line represents case B, where we have the machine and operator. And here we have case A, where we have the foreworker, right? So we have the y-intercept of case A is 0, y-intercept of case B is 1500 for the machine cost. And then we see that the slope for case B is smaller because it's 425, it's cheaper. So case A eventually does catch up since it has a larger slope. And we see the intersect at time is equal to 4 days. Remember that this cost is not, so the y-axis is not representing the cost per day, right? That's represented in the slope. This represents the total cost from that day, from 0 to whatever X number of days. So after 4 days, your investment will already have paid off by the savings that you're having here. So you can look at savings with subtraction of the y value in case B and A. So we can do a lot of things with these linear equations. So hopefully that made sense. And in the next slide, I'll have a short example for you to try. So I'd like you to try using the same exact process. I give you a different application problem, but the concept is exactly the same. So in this concept, we're saying that we have 3 teams, and there are 2 players on each team. And we're going to simplify this greatly just to make this something that you can relate to. Okay, so we're saying that it's a basketball free throw shooting competition, and each team between the 2 players on their team keep switching back and forth and shoot the basketball from the free throw. So everybody shoots the same amount. And on team A, we have 2 advanced players. On team B, you have 2 beginner players. And on team C, you have 1 beginner and 1 advanced player. And to keep things simple, we'll say that the advanced players make 3 out of every 4 shots, and they're consistently making 3 out of every 4 shots. We don't know which of the 4 shots they're going to miss. So we're going to say for every shot they take, they make 3/4 of a point, just to make things simple. The beginner players, every beginner player makes 1 out of 4 shots. And same thing, we'll just say for every shot they take, we'll assume that they earn a 1/4 point, right? Just for the sake of this. Because I want a linear line at the end of the day. I don't want steps, right? The true graph that you would actually get from something like this, would be steps when they make it, and then flat when they miss. So let's say we'll just take the average of all of that. All right, and so your challenge is to create a fair game for these three teams. And the way to give it a fair game is to say that you give teams B and C a starting point advantage. There'll be different starting point advantage because team B is at more of a disadvantage with 2 beginner players. Now the question is, how do you use a linear equation to help you determine what advantage you should give them? And you need to know how many shots this whole game is for. So each team will take 100 shots, so 50 per player. So at the end of 100 shots, you want all three teams to end up with the same number of points, right? That's what we are saying is fair here, right? So assuming every advanced player gets 3 out of 4, every beginner player gets 1 out of 4, what point advantage or starting point advantage would you give team B, and what starting point advantage would you give team C? So I want you to hit pause and work through this problem using the exact same 3 steps that we did earlier. Because first you have to determine what your y and x parameters variables represent, then what your m and b parameters represent, and then finally determine your slopes and y-intercept components. Your y-intercept, I'll give you a hint right now, that's the point advantage piece. All right, so pause this, and then I'll walk you through the steps after you get a chance to try it on your own. Okay, so hopefully you had a chance to try setting up the linear equations for teams A, B, and C. Maybe you had an opportunity to determine the y-intercept or the advantage for teams B and C as well. So I'm going to walk you through that process, see if you got it right. So remember, step 1 is to figure out what the y and x parameters are. So y, am I trying to compare? I'm trying to compare the points that each of the teams get. So y will be in units of points. X will be what gets varied. Well, they're taking shots. So it's not a time component, it's the shots taken, right? Not the points earned, but the shots taken. All right, great. Step 2, the slope. Well, before that, remember, we look at the y-intercept, b. So that, the units of the y-intercept, remember y equals mx plus b, so b's units must match the y set of units. So they need to be points. So when 0 shots are taken, the number of points this team will have will be b. So that's why it's the initial point advantage, right? M, the slope. The average points, I wrote average here because I'm trying to say for like a advanced player, their slope would be 3 of 4. 3 out of 4. So points out of the shots taken. So for every shot, they make 3/4, right? So like I said in the previous slide, I don't want steps. I want to just have an average component. That's why we're going to make this an average points per shot taken. Okay, so now we have to determine the slope and y-intercept for for all 3 of these cases. So we'll start with team A, where we know team A has 2 advanced players. So team A is gonna, from a direct competition perspective, will always beat out team B and C. So we're not going to give them an advantage. So the y-intercept for team A will be equal to 0. Now we need to figure out the slope for team A. Well, they have 2 advanced players. We know they make 3 out of 4 shots. So that's going to be the slope, 3 out of 4. So 3/4 will be the slope. So this one's easy. Linear equation for team A will just be 3/4 x. Y equals 3/4 x, where y is the number of points, x is the number of shots taken. Okay, it's pretty straightforward. Team B. Team B has 2 beginner players. We say the beginner players have 1 out of 4 shots. Make every 1 out of 4 shots. So if we're saying the same for the same reason, this will be 1/4 or a quarter, all right, 0.25 for the slope for team B. Now we don't know what the y-intercept should be for team B, so we'll keep it a variable right now, but we know that that represents the point advantage that team B will get. Do the same thing for team C. Now team C is a little bit trickier because it has one beginner and one advanced player. We know the beginner is going to make 1 out of every 4 shots, and the advanced player is going to make 3 out of every 4 shots. So we know team C's slope should be larger than team B's, but smaller than team A's. So how do we figure out what that slope should be? You might think you just add 3/4 and 1/4, but that will give us 1, or a perfect score, right? 100%. That doesn't make any sense. What you actually have to do is a weighted component. So you say 3/4 for the advanced player and 1/4 for the beginner player, and you divide by number of players, 2. So you get 1/2 for the slope, which is right between team A and team B. Now you might say, well, why didn't we do that for team A or team B's? Well, actually we did, right? So if you look at team A with 2 advanced players, you could have said 3/4 plus 3/4 for the 2 players, and then divide that by 2. Same thing for the beginner players. You could have said 1/4 plus 1/4, and then divide that by 2. So essentially it's the same process. And now for team C, now that we have that, we get y equals 1/2 x plus b as my linear equation. So now I have, for teams A, B, and C, the 3 linear equations. Now we have to figure out what the y-intercepts for team B and C should be for them for all 3 teams to have the same score after 100 shot attempts. Okay, so I have team A, team B, and team C's linear equations. Now I'm trying to determine after 100 shots, or x equals 100, how do I make the y values the same by changing the y-intercepts for teams for teams B and C. Now, I recognize I should have put subscripts for y, x, and b, so we're clear that they're not exactly the same. But I think we're separating these equations well enough that we don't need to do that here. So first thing we got to do is determine after 100 shots, what is case A's value, or you could solve it like we did in the previous one. So however you set that up, that's fine. So I know exactly at x equals 100 is when I want these lines to intersect, so I can plug in 100 here. So 3/4 times 100 is 75 points. So after 100 shots, team A makes 75 points. Team B, after 100 shots, makes 25 points. So in order to match, I know the y-intercept must be 50. And then team C, after 100 points, gets 50 points. So to match, I know the y-intercept must be 25. That's pretty straightforward, right? Graphically, we can see this as well. So there's so team A with the largest slope, team B with the 2 beginners, right, with the smallest slope, so we got to give it the largest advantage. Team C with 1 beginner and 1 advanced player, so we give it, what do we give? 25 point advantage. You can see that after 100 points, team A continues to score higher, so it really depends on when you want these lines to intersect, what the y-intercept should be. Okay, so hopefully this gives you a good sense of how you take word problems, translate them into linear equations, and then compare the linear equations on an intersect application like we do here. There's a lot of different applications that we can also use, but the same process of building up the linear equation should be taken.